In this video I will explain the stress and strain curve in very easy way. So, let's start with basic terms we have used in this curve, which are stress and strain. In tensile test, stress is calculated as load applied to a material, divided by the cross-sectional area of the material. The strain is the deformation or displacement of material due to applied load and can be calculated as change in length divided by original length. In stress-strain curve, the stress is shown along the y-axis, and strain is shown along the x-axis. As we load the testing object in tensile test, it begins to deform and stress continues to raise linearly up to a point A, on this graph. At this point A, if we remove the applied load on the testing object, it will restore to original shape without any deformation. As you can see in this graph, from point O to A, the stress and strain has a linear relationship, and stress is directly proportional to the strain within this region. Beyond point A, the proportionality between stress and strain no longer exists, hence the stress at point A is called the proportional limit. The Hooke's law is valid up to this point only. The slope of this line OA represents the Young's modulus, also known as modulus of elasticity, and it can be calculated as stress divided by strain within proportional limits. Higher slope means stiffer and stronger material, for example high carbon steel, and its curve will look like this. Whereas for flexible material like elastomers, curve will look like this. Remember, these curves are not to scale. With increase in stress beyond the proportional limit, strain being to increase more rapidly for each increment in stress. From point B to C, there is considerable increase in strain without much increase in stress. This is because of plastic deformation in the metal. And this phenomenon is known as yielding. The point B, where this yielding begins, is known as the yield point, and the corresponding stress value is known as yield strength of the material. When the metal is strained beyond the yield point in the region BC, the material experiences a change in its crystalline structure and apparently becomes stronger and more difficult to deform. Thus, an increasing stress is required to produce additional plastic deformation beyond point C. This phenomenon is known as strain hardening. The load eventually reaches its maximum value and corresponding stress at point D is known as ultimate strength or ultimate tensile strength. Further stretching the testing bar, beyond point D, leads to decrease in cross-sectional area of the bar. And it can be seen here. This localized reduction in area is termed as necking. Due to reduction in the cross-sectional area of the bar, load-bearing capacity of the bar reduces drastically, and the curve starts dropping beyond point D. Eventually a point E has reached where testing bar fails. The stress at this point E is known as breaking strength of the material. This curve is known as engineering stress and strain curve, because the stress and strain calculated are not true. The stress calculated based on the original area before the load is applied. In reality, as the load is applied, the area reduces so that the actual or true stress is larger than the engineering stress. And true stress and strain curve will look like this. Hope you really enjoyed this video. Please subscribe my channel for more engineering fundamentals. And don't forget to press bell icon. Thank you.
The tensile test. First test, material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 mm and an original gauge length of 100 mm. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 mm. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Luders effect. After a certain strain, known as the Luder strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL is defined as the force at the lower yield point, Fmax as the maximum force. Using these forces, the strength properties of materials can be calculated. The upper yield strength REH is calculated by dividing the force FEH by the original cross-sectional area S0. The lower yield strength REL is defined in a similar way. The maximum force divided by the original cross-sectional area is called tensile strength RM. In the last step, the tester swings the extensometer back into its resting position and removes the broken test piece. On the work table, he puts the fragments back together again. With the help of the distance marks, the percentage elongation after fracture can be determined. This is the permanent strain after fracture and amounts to about 30% in this example. Please note that the percentage elongation after fracture depends on the length to diameter ratio. By measuring the smallest diameter at the point of fracture, the percentage reduction of area can be calculated. It describes the reduction of cross-sectional area at the point of fracture in relation to the original cross-sectional area. In the second tensile test, a material without yield point phenomenon is to be tested. In this case, it is a precipitation-strengthened aluminium alloy. The test piece has exactly the same shape and dimensions as the specimen in the first test. It is cylindrical, with an original diameter of 10 mm and an original gauge length of 100 mm. After fitting the test piece into the testing machine and panning the extensometer into its working position, the test can start. The initial linear curve in the force elongation diagram again shows the elastic behaviour of the material. But this time, the end of the elastic area is not revealed by a sudden drop of force or any distinct change. There is a smooth and gradual transition from linear elastic behaviour to plastic deformation. In the further course of the tensile test, the force increases and the test piece again is strained uniformly along its length. At the point of maximum force, a neck develops, and all subsequent plastic deformation is confined to this neck until fracture finally occurs there. As a common substitute for the yield strength, the 0.2% proof strength is used. It is the stress that causes 0.2% of plastic deformation in the material. And this is the way to calculate it. First of all, the elongation that corresponds to 0.2% of strain has to be computed. For an initial gauge length of 100 mm, the result is 0.2 mm. In the force elongation diagram, a straight line parallel to the elastic line is drawn through the offset point of 0.2 mm of elongation. The force at the intersection point of the offset line with the force elongation diagram is designated as Fp 0.2. This is the force that causes a plastic strain of 0.2%. The 0.2% proof strength, Rp 0.2, is equal to Fp 0.2 divided by the original cross-sectional area S0. Tensile strength, percentage elongation after fracture, and percentage reduction of area are calculated in the same way as in the first test.
Hi friends, today we are going to conduct compression test. Aim of this experiment is to conduct the compression test on this mild steel specimen. Apparatus required are UTM, that is universal testing machine, test specimen, vernier caliper, steel rule and extensometer. According to ASTM, that is American Society for Testing and Materials, mild steel specimen of 12.7 mm diameter and 25.4 mm length is used. Approximately, we are using the specimen with same dimension. Now, we will conduct the compression test. Procedure: firstly, we measure the length of specimen and its diameter by using vernier calipers. Compression attachment is fixed on UTM, that is Universal Testing Machine. Specimen is kept at the center of the crosshead so that uniform loading can be assured to the specimen. Movable crosshead is used for applying load and it is lowered slowly until it touches the specimen. The extensometer is fixed and readings are fixed to 0 so that when any load is applied, the change in extensometer reading can be taken. Load is applied gradually by opening the valves and by pressing the start button. Amount of load being applied can be seen in dial gauge whose least count is 5 kN. As the load is gradually applied, the extensometer reading are taken at equal intervals of load until the specimen fails. The extensometer reading gives the change in length of specimen due to compressive load and corresponding load by deflection curve can be plotted. As we know, ductile material shows more deflection, hence the load is gradually applied and this can be observed in the dial gauge with the help of red and black pointer. Loading is continued till it reaches elastic limit. Beyond the elastic limit, plastic region starts. Once the elastic limit is reached, it can be observed that mild steel specimen is bulged out and the pointer stops for a moment with a small jerk and tends to move backward direction, which is an indication that specimen has reached its elastic limit or yield point. But it cannot be clearly seen as in tension test since it is a compression test. The final length and diameter of the specimen is calculated by using vernier caliper. The load compression curve is drawn and the shape of the curve for the L/D ratio can be noted. An enlarged diagram of load compression curve for the initial portion is drawn on the same graph sheet. Slope of the straight portion gives the Young's modulus. 0.2% proof stress. Since the yield point cannot be identified in a compression test, it can be obtained by drawing a line parallel at a distance of 0.002 times the original length. Compressive strength is given by the maximum load at failure to the original cross-sectional area. The percentage expansion in area can be calculated as the change in area to the original area. The percentage reduction in length is given by the change in length to the original length. With this, we come to the end of the compression test. Thank you.
नमस्कार दोस्तों, मैं प्रकाश कुमार सैनी। मैं आज आपको बता रहा हूं दोस्तों यूटीएम मशीन पर कंप्रेशन टेस्ट किस तरीके से किया जाता है। तो हमारे पास एक क्यूब है, ये कंक्रीट का क्यूब है। इसके द्वारा हम इसकी स्ट्रेंथ चेक करेंगे, कितना इसकी स्ट्रेंथ है इस क्यूब की। ठीक है, यूटीएम मशीन पर कंप्रेशन टेस्ट करेंगे आज आपको। इसके बाद मैं आपको टेंसाइल टेस्ट करके बताऊंगा। तो यूटीएम मशीन क्या होती है दोस्तों? यूटीएम मशीन क्या रहता है? यूनिवर्सल टेस्टिंग मशीन का उपयोग अधिकतर किसी भी मटेरियल की स्ट्रेंथ चेक करने के लिए किया जाता है। ठीक है ना। अब यूटीएम मशीन के ऊपर एक से ज़्यादा इसके अंदर टेस्ट परफॉर्म किया है, कंप्रेशन टेस्ट, बेंडिंग टेस्ट, शेयरिंग टेस्ट, टेंसाइल टेस्ट। तो इस तरीके से इसकी डिज़ाइन इस तरीके से बनाएगी ये एक से ज़्यादा टेस्ट परफॉर्म कर सके, इसलिए इस मशीन का नाम यूनिवर्सल टेस्टिंग मशीन कहा गया दोस्तों। अब यूनिवर्सल टेस्टिंग मशीन के ऊपर कौन कौन से पार्ट्स लगे रहते हैं उसके बारे में आपको जानकारी दूँ। तो सबसे पहले यूनिवर्सल टेस्टिंग को 2 भागों में बांटा गया है। पहला भाग रहता है दोस्तों कंट्रोल यूनिट, सेकेंड भाग रहता है आपका लोडिंग अरेंजमेंट। तो ये लोडिंग अरेंजमेंट रहता है उसके ऊपर बहुत सारे पार्ट्स लगे रहते हैं। उनका क्या काम रहता है? इस तरीके से कंट्रोल यूनिट लगे रहती है, उसके अंदर कौन कौन से पार्ट्स उसके बारे में आपको जानकारी। तो ये लोडिंग अरेंजमेंट रहता है, इसके अंदर ये रहता है, ये मिडिल क्रॉस हेड रहता है, ये अपर क्रॉस हेड रहता है और ये लोअर क्रॉस हेड है। तो ये मीडियम क्रॉस हेड रहता है, ये क्या रहता है? फिक्स रहता है। ठीक है ना। इसके ऊपर 4 कॉलम लगे रहते हैं, 2 कॉलम थ्रेड वाले रहते हैं और 2 कॉलम प्लेन वाले रहते हैं। जो थ्रेड वाले कॉलम रहते हैं वो तो उसी के ऊपर इंटरमीडिएट क्रॉस हेड अप और डाउन मोशन में इस कंट्रोल यूनिट से करते हैं हम। ठीक है, ऊपर नीचे लाते हैं इसको। इसके बाद जो 2 प्लेन वाले लग रहा है, इनमें क्या रहता है? ऑयल का प्रेशर आता है, ये रैम ऊपर उठती है, ऑयल के प्रेशर की वजह से ये रिम ऊपर उठती है, इसकी वजह से अपर क्रॉस हेड और लोअर क्रॉस हेड ऊपर उठता है और ये फिक्स रहता है तो इससे टकराता है, तो ये कंप्रेशन टेस्ट होता है। इसी तरीके से ये ऊपर जाती है तो टेंसाइल टेस्ट होता है। तो मैं टेंसाइल टेस्ट करके, अब इधर की साइड आओगे तो ये क्या रहेगा दोस्तों, कंट्रोल यूनिट है, इसके ऊपर अप और डाउन वाले स्विच लग रहे हैं, ठीक है। इसके बाद इसके पंप को चालू करने और उसको कंट्रोल करने के लिए पंप का ओपन और क्लोज वाला वाल्व लग रहा है, ये डायल गेज रहता है दोस्तों। इसके ऊपर कितना टेस्ट फोर्स अप्लाई हो रहा है, लोड अप्लाई हो रहा है, तो डायरेक्ट डायल गेज से पता कर लेंगे। तो सबसे पहले हम इसको 5 मिला के इसको सेट कर लेता हूँ। ठीक है, अब क्या कर रहा हूँ मैं, इसको चालू कर रहा हूँ, ठीक है। चालू करने के बाद सबसे पहले इसको वाल्व को क्लोज कर देते हैं, इसके बाद धीरे धीरे इसको ओपन करेंगे और यहाँ पर फिर डायरेक्ट लोड आएगा। ये दिख रहा होगा, आप डायल पे देखना कितने लोड पर ब्रेक होगा ये आपके 320 किलो न्यूटन के लगभग इसके ऊपर लोड लगा। इस तरीके से ये ब्रेक हो जाता है दोस्तों। मैं इसको पास में ले जाके आपको बताता हूँ किस तरीके से ब्रेक हुआ। देखो, तो इसका जो कंप्रेसर लोड हुआ है वो आपका ये वाला पॉइंटर यानी 390 के लगभग इसका ये लोड पर ब्रेक हुआ। तो दोस्तों मैं आशा करता हूँ ये वीडियो आपको अच्छा लगा होगा। मैं प्रकाश कुमार सैनी, जेपी यूनिवर्सिटी गुना मध्य प्रदेश। थैंक यू फॉर वाचिंग दिस वीडियो। यदि ये वीडियो आपको अच्छा लगे तो लाइक करना, शेयर करना, सब्सक्राइब करना। थैंक यू।
Hello viewers, one of the important properties of concrete in its hardened state is its compressive strength. Compressive strength of concrete is important because other strengths such as flexural, bond and resistance to abrasion improve with increase in its compressive strength. The compressive strength of concrete depends upon the proportion of ingredients used in concrete. It is therefore important to find the strength of concrete using different proportions of ingredients to meet the structural requirements. In this video program, we shall demonstrate the procedure for casting and testing of cement concrete cubes. The equipment and accessories required for making the concrete cubes and testing them for their compressive strength are cube molds of 100 mm or 150 mm size with IS mark. We are using 150 mm cube molds in this case. Electronic weighing balance, GI sheet for making concrete, vibrating needle, compression testing machine of capacity 100 tons, 200 tons or 300 tons depending upon the grade of concrete of which cubes are to be cast, and the observation sheet to record the readings. For casting the cement concrete cubes, measure the dry proportions of ingredients as per the design requirement. For example, in this case, the proportions used for casting cubes are 1:1.5:3 as per Indian Standard Code 456/2000. The dry ingredients are then thoroughly mixed so as to obtain a uniform mixture. The proportion of different ingredients taken should be sufficient enough to cast 3 molds. Take the designed quantity of water. Add this water to the mixture. Mix the ingredients thoroughly so as to obtain concrete with uniform texture. Using the scoop, fill the concrete into the molds. It is then compacted by means of needle vibrator, ensuring thorough compaction of concrete. After the top layer has been compacted, the surface of the concrete shall be finished level with the top of the mold using a trowel. It is tapped well till the cement slurry comes to the top to give it a well finished appearance. After some time, the molds are covered with wet gunny bags and left undisturbed for 24 hours at a temperature of 27 plus minus 2 degrees Celsius at 90% relative humidity. After 24 hours, the specimens are removed from the mold. They are then taken to be kept submerged in clean, fresh water at a temperature of 27 plus minus 2 degrees Celsius. The specimens are kept in the water either for 7 days or 28 days. Water in which specimen is submerged should be renewed after every 7 days. Specimens, when received dry, should be kept in water for 24 hours before they are taken for testing. The cubes are taken out of the tank just half an hour prior to the test. The specimen to be tested for compressive strength should be in surface dry condition. This is the compression testing machine where the concrete cubes are tested. The capacity of this machine is 300 tons. For testing the compressive strength of cube, it is centrally placed in the loading unit. The load shall be applied to opposite sides of cubes as cast. The axis of the specimen shall be carefully aligned with the center of thrust of the spherically seated platen. Now, slowly apply load at the rate of 140 kg per centimeter square per minute till the cube breaks. The maximum load at which the specimen breaks is taken as the compressive load.
গাড়িতে সুবিধা আছে, গাড়িতে আপনি রাস্তায় না থাকলে গাড়িতে কোনো প্রবলেম নেই, বসে আছেন না, ভয় করে অন্য গাড়ি এলে, রাস্তায় কিছু নেই, পরিষ্কার।
It is 90 tons in this case, recorded in the observation sheet. The compressive strength of the specimen shall be calculated by dividing the maximum compressive load taken by the specimen by its cross-sectional area. Compressive strength shall be equal to compressive load divided by the cross-sectional area of the specimen. The cross-sectional area of 15 centimeter cube is 15 multiplied by 15 centimeter, which is equal to 225 centimeter square. Since the compressive load is 90 tons, the compressive strength of the cube shall be equal to 90 multiplied by 1000 divided by 225, which comes out to be 400 kilogram per centimeter square. Average of 3 readings shall be taken as the representative of the batch. In the present video program, you have seen the apparatus and the experimental procedure for casting the cubes, curing of cubes, and determining the compressive strength of concrete cubes. Since compressive strength is the most important property of concrete, it is therefore necessary that utmost care must be exercised in measuring the compressive load. As per Indian Standard Code 516, the individual variation in compressive load should not be more than plus minus 15% of the average value. If the variation is more, repeat tests for the same concrete must be made. I hope after having viewed this video program, you shall be able to perform this experiment in your laboratory. Thank you.